The melting of rocks with the binary eutectic phase diagram. The melting of rocks is different with the normal chemical composition in our neutral life. The melting rocks refers to a process by which rocks undergo the partial melting leading to the formation of magma. This process is crucial in the Earth's crustal evolution, contributing to the creation of both oceanic and continental crust. The textbook discussed the melting of rocks in the context of the binary eutectic phase diagram, using the example of the diaplaside and anthracite diagram. The binary eutectic phase diagram illustrates the melting behavior of a mixture composed of two distinct solid phases and a liquid phase. The diagram represents the proportion of each mineral in the mixture on the x-axis, which is here, and the temperature on the y-axis. The system consists of two minerals, diaplaside, Di, and anthracite here, with distinct solid phases that do not form a solid solution. Each pure mineral melts at a single temperature, and all the other compositions along the axis represent the mixtures of two minerals, the proportion of the two compositions. The diagram has a solidus which marks the beginning of melting, and a liquidus indicating the completion of melting. And here we see the eutectic point here. The first liquid appears at the eutectic point here, representing the minimum melting temperature for the all mixtures. As the liquid forms, the solid composition becomes relatively depleted in Di, this one, causing its composition to move along horizontal axis towards the anthracite axis, this. The system remains partially melted between the solidus and liquidus until the last crystal of Di melts out, resulting in a composition of 30% liquid and 20% anthracite. And the remaining anthracite begins to melt, causing the liquid to become more An rich. The proportion of anthracites become more and move from L1 to L2. The system becomes entirely liquid when the liquid composition arrives at the bulk composition here, dissolving the last crystal of An. And throughout the melting process, the liquid composition L1 to L2 always differs from the bulk composition until the system is entirely liquid. Melting occurs over a range of temperatures, allowing the partial melting, segregation, and separation of liquid from solid. And the next one is the solid solution phase diagram. The textbook provides an explanation of the melting rock's behavior using the example of a solid solution phase diagram. The example is the violite and forsterite. The solid solution phase diagram illustrates the principle of melting in a system where there is a solution in both solid and liquid phases. It represents the variation and composition between pure fosterites and pure ferrites. An arbitrary bulk composition is chosen, represented by a vertical line with an arrow on the diagram. This bulk composition is a mixture of fosterites and ferrites in varying proportions. Temperatures below the solidus represent where only solid olivine is present. And as the temperature rises, the bulk composition reaches the solidus, and the first liquid appears at S1 with a specific composition. The system follows a path to S1 to S2 in the solid phase and from L1 to L2 in the liquid phase as the temperature continues to increase. And when the liquid composition reaches the bulk composition, the system becomes entirely molten, and further heating causes the liquid to rise above the liquidus into liquid field. And the textbook emphasizes that the phase diagrams are for experimental data determined at 1 atmosphere pressure. Higher pressures stabilize denser solid phases relative to lighter liquids, requiring higher temperatures for melting. It mentions that pressure reduces melting, which occurs on Earth when mantle material rises. As the mantle ascends, pressure decreases, and when it crosses the solidus, melting will begin. Does the mantle cools down or heats up as it melts, and why? The mantle cools down as it melts, and this is due to the process of pressure release melting. Contrary to our common experience of melting through the application of heat and the raising of temperature, the mantle undergoes melting as it rises and experiences a decrease in pressure. The ascent of mantle material is associated with a reduction in pressure, allowing the mantle to reach a point where it crosses the solidus. Melting then begins as the mantle continues to rise. It encounters progressively lower pressures, leading to an increase in the extent of partial melting. In the Earth's mantle, melting occurs as the result of the mantle cooling down due to pressure release.
Very good. It covered what I expected to be presented regarding the topics.
May I ask you the first diagram? I want to ask you where the pressure influence the curve. 就是它测量的背景压力是怎么样？
The textbook write that at the natural atmosphere.
Pressure.
Yeah. I didn't see that the atmosphere affects the diagram.
Correct. You cannot see the influence of pressure in this diagram because it's done at a constant pressure. If you want to see influence, this axis has to be pressure. However, the y-axis is temperature. So it's measured at a constant 1 atmospheric pressure.
How do you calculate the proportion between the 左边跟右边的比例？
Hardy asks, how do scientists know the proportion? Because if the rock or the mineral melt, how do scientists determine its proportion? The minerals, they have different cations. By measuring the cations, they can back calculate the proportion of different minerals. Okay,
Today I'm going to present assignment 8B. She's explained the timing of core mantle segregation using the evidence of hafnium-tungsten isotope pair. First, we are going to talk about the theories on Earth's accretion. One of the driving questions about the Earth's accretion is whether the metal core preceded the other layers or if the original Earth was a melting pot of elements that differentiated afterwards. The first model is called the heterogeneous accretion and suggests that the metals came first and then the various elements from our vicinity came to form the outer layers subsequently. The second element model, called the homogeneous accretion, suggests that the elements were first homogeneously accreted and then separated with gravity or cooling. By studying the chondrites and the timing of cooling of different elements, heterogeneous accretion is highly improbable because calcium and aluminum-rich elements were first to solidify, and in order to have a metal core on which other layer accreted, they must have been the first one to solidify, if we follow the heterogeneous accretion model. So we are going to talk about the affinity of hafnium and tungsten and the logic of using them. Each element is found in different proportions through the layers of the solid Earth. Magma-filled elements are concentrated in liquid silicates, thus they are easily transported through the mantle to the crust, where they accumulate in higher concentration, so we can see them here, the crust. Lithophile elements prefer silicates rods and accumulate in mantle. Siderophile and chalcophile prefer metallic states or sulfur-bearing minerals and thus accumulate in core. There is also atmophile elements which are very volatile and are found in liquid or gases, but since they are not present in solid earth, we are not using them. Using this knowledge, we can observe that tungsten is a siderophile element, which is almost completely present in the core, around 80%, where hafnium is a lithophile element, almost completely present in mantle, around 90%, and a little bit in crust. Tungsten being the daughter of the radio element hafnium, which has an half-life of 9 million years. Analyzing its concentration in each part of the solid earth and comparing it to the concentration of chondrites that cooled slowly will tell us if the core formed slowly or rather quickly. Since hafnium is lithophile, it cannot be contained in the core and thus remained in the bulk, where there is a throw of balance in the tungsten 182 and tungsten 183 ratio. Now we're going to explain this figure. By using the property of chondrites, we can get a graph of the evolution of the ratio of our two isotopes of tungsten, which is directly proportionate to the decay of hafnium. If the concentration is the core and the bulk silicate earth has been similar, it would have meant that the core creation was older than 100 million years ago, because the vast majority of this decay pair would have been decayed and the ratio would have been the same. However, we can observe since 30 million years after the formation of the Earth that the ratio has remained the same in the core, while it has increased a lot in the bulk. Since hafnium is lithophile, it has been unable to be present in the core, and thus further destabilizing the ratio of our isotopes in the mantle, which means the core differentiated around 30 million years after the formation of the Earth.
In this graph, do you think the scientists could have samples from the core, or they make their argument mainly based on mental samples?
Only mental.
Do you agree, Axel?
Yes.
Why you think Mayfield element is concentrated in liquid silicate?
Because I read it. I think magma-filled elements are easily melted, so they are easily transported to the crust where they are cooled.
If you read this figure, you will see it's thorium, uranium, lanthanum, cerium, thallium. These are several of them are the uranium series isotope or elements you have seen. A common feature of them is in terms of ionic radius, they are generally big. Their concentration in crust may not be high. However, in terms of the proportion in crust compared to mantle and core, they are high. Because when the mantle rock is melted, these large ions, they are preferentially melted because they are not that well fitted into the mineral structures. So when the mineral is not stable, they will be gone first. Because we are talking about hafnium and tungsten isotope pair, what is the hafnium isotope atomic mass?
182.
So what's the role of 1H3 tungsten here?
It's a stable isotope. It's like the previous strontium that we used, but I don't remember exactly the reason. I thought it was to make the data simpler. I would guess that every time you have to use some radio element, you always use a stable isotope for reference, but I don't remember why.
There's a confusion why we always want to divide the value by a stable isotope. The first trick is always with the isotopic ratio. The good thing is you can measure it more accurately. That's the first advantage. And then in this case, you want to compare your mantle sample with chondrite, which is not segregated solar system material. In this graph, the result shows you that the bulk silicate earth or the mantle sample has a higher tungsten 182 to 183 ratio. The concentration of 182 depends on how much hafnium 182 was there initially in your sample. That is something you have very loose control. You don't know that. However, we know that tungsten 183 is stable isotope and is not produced by another radioactive isotope. So it is reference material. When you divide tungsten 182 to tungsten 183, you are talking about whether our mantle sample is relatively enriched compared to chondrite. You are not talking about absolutely enriched. You are talking about relatively enriched. Because the absolute enrichment depends on how much hafnium, 182, the sample had at the beginning. It may happen that maybe the earth and the chondrite that you compare with simply have different hafnium 182 at the beginning. If you want to compare that, you will stand at a different starting point. Then the scientists say, okay, we use tungsten 183 as a reference point. If this ratio is indeed higher in the mantle sample, then yes, it is really enriched in the mantle. So that's the logic of using isotope ratio instead of isotope concentration. Starting from this week, we have 3 weeks of solid earth. And this is the first part, interior segregation. How do we know the interior? Can we have core sample? No, we never have core sample. So you have to make guess. These are the methods you can know the interior. You can do it from density. We talk about this when we talk about planetary system. Inertia, I will skip this. Seismology, geological observation, experimentation, geochemistry, cosmochemistry. Earthquakes or seismic waves are the major approach we use to understand the interior of the Earth. Because earthquakes can cause many different kinds of waves. You can experience 2 types of wave. They are the so-called P wave and S wave. You will experience one direction first and then the other direction. P wave is the first one to come. The way the ground will move is parallel to the propagation direction of the wave. So it's moving like this. It will come faster. And the other is shear wave. It's moving like this. So it's perpendicular to the propagation direction of the wave. It will be slower. If you are lucky enough, you will also experience the high-tech in Taiwan. Seismologists in Taiwan, based on the special property of the P wave, have developed an alarming system. So you will probably get the alarm 5 seconds before the wave comes. So you will have a chance to look for a place to hide. 5 seconds, huh? I don't know if you have seen this before. This is a very famous feature of P wave and S wave. When an earthquake happens, especially a big one, not only in Taiwan that you will experience the wave, but actually the whole globe will experience the wave because the wave will propagate all the way around the Earth. Any place on Earth can detect that earthquake. Therefore, you know that some observatory in US or in Japan or elsewhere, they detected this earthquake and determined the epicenter and the magnitude. The good thing of this global network of earthquake observatory is people can use the seismic wave to map the interior of the Earth. They realize that for the propagation of the P wave and the S wave is not straightforward. When scientists use the arrival time to back calculate the propagation speed, they realize that in the interior of the Earth, P wave will undergo some complicated deflection. So you see deflection here? And because of that deflection, when a P wave happens here, there is a certain area on Earth where the observatory cannot detect this earthquake. In terms of P wave, it is 105 degrees to 140 degrees away from the epicenter. There will be 2 regions. They are symmetrical from the epicenter. For the S wave, this area will be much larger. For the area that failed to detect this specific earthquake, this is the shadow zone, region where no waves appear of this earthquake. And for S wave, the shadow zone is 105 degrees from one side to the other side. So 105 means from here to here. It's a very broad zone where you cannot detect that specific earthquake. Which layer of the Earth is associated with the formation of shadow zone?
Outer core.
Very good. Outer core. The outer core is the key structure that has deflected or eaten up the seismic wave and prevented it from being detected. Now I will just repeat some of the basic property of P wave. P wave can propagate through both solid and liquid. For P wave, they have two narrow shadow zones. The reason why there are shadow zones is because of wave refraction at the mantle upper core interface. But for S wave can only propagate through solids. Therefore, reason for the shadow zone is wave die out. Die out means the wave simply cannot penetrate through a specific layer of the Earth structure because liquids or fluids do not sustain shearing. Therefore, scientists have used the shadow zone to map the core mantle boundary. That's the first thing they can do from the seismic wave. And the second thing they know from the seismic wave is the outer core must be liquid. You have seen different versions of this graph, maybe in your high school or science course. We know they are different structure, but the reality is what scientists originally have is this density, and this value is back calculated from the seismic wave velocity. That's what they have at the beginning. They have seismic wave velocity. Seismic wave velocity will change depending on two parameters. The first is whether the matter is solid or fluid, the phase of matter. And the second is the density of the matter. Even if the matter is all solid, denser material will allow for higher velocity. So phase and density will affect seismic wave velocity. Based on that, scientists was able to depict the internal structure of the Earth. We know the first one is mole hole. And mole hole at the oceanic crust is about 7 kilometers. So some international drilling projects have been targeting mole hole for more than half a century, but still no success. It's difficult to drill that deep. The second is Gutenberg, discontinuity. And the last one is Lehman, discontinuity. That's the three discontinuity. And here there are some crucial density value that you want to roughly know. The first is continent. When I talk about planetary systems, I already mentioned that for students who want to continue to study marine sediment, there's a value you should keep in mind, which is the density of marine sediment. We will give you a value of 2.6 to 0.7. This corresponds to the density of continent because all the sediment you see, especially the clastic material, is weathered product from continents. So we use the density from continents. And for continents, the major chemical composition is SiO2, silicon. That means you mainly have quartz and feldspar. If we go all the way to the contrast mantle, the principal mineral is olivine and pyroxene. Then you see its density is 3.3. From 3.3 to 2.7, is this density difference large? I guess you don't think so. If you have two pieces of rock with the same volume, one is from the continent, the other is from mantle, will you be able to differentiate the mass difference with your hand? I guess not, right? However, next week we will talk about how important the density difference is. This density difference is actually huge. And the other thing you immediately notice is the chemical composition. The silicon decreased from 70 to 44, while magnesium oxide increased from 1 to 39. It's a huge difference. Such huge difference is caused by partial melting of rock. And of course, this corresponds to Bowen series. This is the slide from mineral chemistry lecture. This is a short review of different silicate structure, whether they are high temperature mineral or low temperature mineral, whether they are prone to weathering or weathering resistant. Here, there's a question. This is the density of different part of the Earth. For the continents, here it says 2.8. but usually we say marine sediment is 2.6 to 2.7. And the density increase toward the interior of the Earth. For the upper mantle is 3.3, lower mantle 4.2, down to the inner core it's up to 12 to 13. How to explain the very high density of the inner core? Because below are the density values of different metals. You all know that the core is made of metal, mostly iron and some nickel. These are the density of iron, nickel, and we also have copper, silver, gold, platinum. This is the density of the core. It's from 10 to 13. These values are derived from the seismic wave propagation velocity. Does it mean that the interior of the core is made of something like a silver and gold?
因为地核的压力，就是因为压力的关系，把它变成压实。
我觉得是因为压力吧，就是因为压力。
Exactly. The density that you know from the periodic table is the density at 1 atmospheric pressure. Density is not always constant. If you change the pressure, the density will also change. That's a reason why the density you know at 1 atmospheric pressure cannot explain the density derived from seismology. Because pressure is a main controlling factor for the observations you made for the Earth, especially the interior of the Earth is highly affected by the factor pressure. So yes, the interior of the core is made of iron and nickel. However, at high pressure, their density will not be this value. Their density will be much higher than this value.
所以才会有测到这个12到13。
So now we know the bulk parameter of the different layer. We know their density from seismology. The next question is, how do we know the chemical composition of each layer? We need to quickly go through these different files. These files. Atmo file means it loves ocean and atmosphere. Magma file means the element loves silicate melt, which means magma. We also have lithophile, siderophile, and trachyphile. This is for metal and this is for sulfur. We are going to talk about a few examples. You know this very well because for students at this department, you deal with these light elements like carbon, nitrogen, oxygen, noble gas, hydrogen. They are relatively concentrated in the ocean and atmosphere. But for the majority of the Earth, it is a different story. For the lithophile, which will be mainly in the mantle and crust, we have to deal with silica, oxygen, magnesium, calcium, aluminum, and titanium, especially titanium. Titanium is considered a very good indicator of terrestrial element. For siderophile, we know there must be iron. There is also nickel, gold, silver, copper. They are relatively abundant, and unfortunately, they are rare for the crust. That's the reason why the three here, gold, silver, copper, platinum, they are expensive for us. Trachyphile, I will not go into detail of them. The most interesting part is magma file. When you look at this, I don't know if this ring a bell because you have learned this. Rubidium strontium, we learned this from the first course about dating. And uranium, thorium, lead, we learned this from the course uranium series chronometry. These radioactive isotopes, they are relatively enriched in magma. The continental crust, they are all produced by magma. Therefore, these elements are relatively enriched in the continental crust. The affinity of elements together with density, seismic velocity, and geochemical data allow scientists to derive the elemental composition of different layers. Based on what we talk about, the affinities of different elements, we can estimate their relative distribution in crust, mantle, and core. So this is relative distribution from 0 to 1. We can also derive the elemental composition of bulk Earth. This is the composition of the bulk Earth. We just look at a few of them. We don't need to look at all of them. Most of their unit is ppm, unless noted. So these four, they are in percent. The most abundant element is iron, but you cannot see it. It's at the very interior part of the Earth. The second most abundant element is oxygen. It's relatively abundant because it forms silicate minerals, so it's abundant. The third is silica. The fourth is magnesium. We always say the four major elements of the Earth is iron, magnesium, silica, and oxygen. For the element that people in this department care about, such as carbon, is actually quite minor, only 730 ppm. Once you know the affinity of different elements, you can make use of them. That's one of your assignments. You can look for radioactive isotope pairs with the parent and daughter having different affinity. You can use them to study the evolution of the Earth's layer. In your assignment, we work with hafnium, which is a lithophile, and tungsten, which is a siderophile. We use this isotope pair to study the evolution of the Earth. That would be the next part of this lecture, the origin of Earth's core. Even for students at the geology department, the Earth's core is a very elusive, distant concept. You will have the feeling that you have nothing to do with the core because it's so distant, you cannot sample it. In Taiwan, at the Academia Sinica, there is a scientist who studies core. You may ask how this is done. How do you study the core? The answer is he has to use the so-called ultra-high pressure simulator. How do you achieve ultra-high pressure? He needs to use a special kind of experimental instrument called 钻石粘. It's a very special instrument, and the experimental space is very, very small because you need to create ultra-high pressure. You can use some special spectroscopy to analyze the chemical reaction that takes place within the 钻石粘. It's very fancy. Talking about the origin of the core, in your assignment, I asked you to first present what are the scenarios for the segregation of the Earth. The first is heterogeneous accretion, which means metal comes first, silicate comes second, and lastly, gas and water. We also have homogeneous accretion, which is everything comes together, like this, and then they get separated over time. Scientists have tried to do some experiments to figure out whether the heterogeneous accretion makes sense. How do scientists do that? They do a condensation experiment. The idea is if the Earth is accreted over time, during accretion, it will gradually cool down. When you think backwards, the first thing that accreted must be something that has the highest melting point. Therefore, because of its high melting point, when temperature is lowered, it will be the first thing to condense. So scientists mix everything together, heat it up, and then cool it down. They study what is the first thing that will get condensed. What they find is, at this temperature, tungsten is the first to condense. Second, aluminum, titanium, and calcium in this form. Iron and nickel, they are the third to condense, and so on and so on and so on. This doesn't really match what we know from other lines of evidence. From meteorite, we know the core should be made of this. However, according to the experiment, our core should be made of tungsten, which doesn't really make sense because in meteorite, there is never a huge amount of tungsten. The result doesn't really support heterogeneous accretion. Therefore, scientists believe that at the beginning, it should be homogeneous accretion. And then The core formation is the result of the great metal silicate separation. So the separation happens next. Why did the separation happen? Scientists believe that there are two characteristics that will result in the separation. The first is density. The second is immiscibility. What is immiscible? You must have your daily experience when you drink a cup of soup. You will see oil droplets at top of your soup. The oil will not really blend in the soup because oil is immiscible with water. So this is called immiscibility. These two concepts are very different. I will use some cartoon to explain the difference between these two concepts because these two concepts are easily mixed up. I have a bottle. Here we have density difference. We have fresh water, its density is 1. We have seawater, which has a density of 1.2. In seawater, we have more sodium ion. Here we have different density. What happens if you shake? I think you can easily imagine what will happen. They will totally mix up. So we say they are miscible. They can be well mixed. If the volume ratio is 1:1, you can imagine that the ultimate solution is brackish water with a density of 1.1, and sodium ion will also evenly distributed. What about very density and immiscible, which would be like this? Instead of fresh water, here you have oil. Oil has a density of 0.8. Below, you have fresh water, which has a density of 1.0, and you have sodium here. Sodium cannot be easily dissolved in oil. Now, you shake, what will happen? I don't know how many of you have this experience of shaking oil with water. In my lab, we do this very often because usually this is not oil, this is organic solvent. When you shake, at the beginning you see they look like miscible because you will see some turbid mixture. However, maybe after 1 minute, they will be separated again. No matter how hard you shake it, they will always separate because they are immiscible. They will again follow their nature, which is their density. Oil will always be at the top and water will always at the bottom. And sodium here will stay with the fresh water, never with oil. That's the difference between this concept. Come back to the metal silicate separation. Now you have to think of them as this. At homogeneous accretion at the beginning is a little bit like this. At some point, they will follow their nature and start to separate. Evidence from meteorites suggests that this separation is a common planetary process. We have 3 kinds of meteorites, and there is a special kind of meteorite called iron meteorite. It's made of almost pure iron-nickel alloy. From this kind of meteorite, we know the separation is very common. It's not just for the Earth. As long as the planetary objects has a certain size, this will happen. Then you might ask, how fast is core mantle separation? Scientists have tried to answer this question, and that's the assignment, the hafnium tungsten isotope pair. Did core formation happen instantaneously after accretion, or is it a progressive process that is still going on today? Is it still going on today? When you are talking about liquids, like organic solvent versus water, you shake, they will almost immediately separate. You have no problem understanding that. However, now we are talking about solid. Do they also separate quickly? That's something that needs to be investigated. It's not that intuitive. That's why scientists use hafnium-182 and tungsten-182 isotope pair with tungsten-183 as the stable isotope. The half-life is 9 million years, and one is lithophile, the other is siderophile. I use this graph to explain this. Here, we have hafnium-182, and we also have tungsten-183. if the core mantle segregation is a very rapid process, because tungsten 183 was there already at the beginning, when the segregation happened, tungsten 183 will enter the core because it is a siderophile. While hafnium 182, which is a lithophile, will stay in the mantle, and then it will take time to decay to tungsten 182. That's one scenario. The other scenario is at the beginning we have hafnium 182 and tungsten 183. This will decay to tungsten 182. If the segregation is a slow process, how slow is it? Longer than 10 half-lives. The half-life of this isotope pair is 9 million years, so we say 90 million years is the utility, so we give it a full number, 100 million years. If the segregation is a slow process and even after 100 million years it is still going on, over time, tungsten 182, which is derived from hafnium 182, will go together with tungsten 183 to the core. The hafnium 182 at the end will close to zero because it is a very short-lived isotope. Actually, hafnium 182 is an extinct isotope. So then, what if you take a sample from the mantle, measure its tungsten 182 to 183 ratio? Which one will give you a higher ratio? The answer will be this one. Because in this case, tungsten 183 goes first, and tungsten 182 is produced later. Therefore, most of the tungsten 183 will be away from the mantle. When you measure tungsten 182 to 83 ratio, the sample at the mantle here will give you higher ratio. While in this case, tungsten 183 and 82, they always go together. Their ratio will be higher. This is years after time zero. Time zero means the time when the Earth was accreted. And this is the tungsten 182 to tungsten 183 ratio. This curve is chondritic, which means chondrite. We always want to compare with chondrite. Why is that?
Because chondrite is from the galaxy, and so 它没有被改变过。
Close. Because chondrite has not undergone any planetary process. It has not undergone any separation. Therefore, you can think of it as a raw material that has not been processed at all. So we compare with chondrite. In chondrite, the ratio will increase over time because hafnium 182 will decay over time. At some point, the ratio will level off when most of the hafnium is decayed. This is the curve for bulk silicate earth. That would basically mean mantle. In mantle, we found even higher ratio than chondrite. That means tungsten 183 has entered the core. That would be the most reasonable explanation why mantle has higher ratio here, because tungsten 183 is here. If today we can sample the core will have lower ratio than chondrite. Overall, this needs to be balanced. This supports the scenario that the core mantle segregation is like this. After shaking, they separate also very quickly. This time, around 33 million years after the Earth's accretion, is nothing compared to the lifespan of the Earth. Now we quickly go through the crust. The Earth's crust is formed by ongoing separation of silicate materials by partial melting. The crust is still being produced by partial melting. Mixture of molecules that form solutions in the liquid state will melt over a range of temperature, not one temperature. For example, salt and water. And melting points are pressure dependent. The higher the pressure, the higher the melting point. This is not just for silicate, it's actually for everything. The liquid, which is the melt or the magma, the liquid composition will vary with temperature. Solidus is the line that separates solid from the first appearance of liquid. So you can think of it as the first melting temperature. And liquid dust is the line that separates liquid from the last grain of solid. You can think of it as the last or the highest melting point. From your assignment, you know there are two kinds of melting behavior. One is binary eutectic phase diagram. The other is solid solution phase diagram. So what's the difference? If now I have a piece of granite, I heat it up. Which one would it go?
Solid solution.
Oh, that means you have not really understand the difference between the two. The answer is binary eutectic phase diagram. Why? When you see granite, do you see mineral particles? If they are just a mixture of mineral grain embedded together, mineral A does not dissolve mineral B. They are actually separate. Their melting behavior will follow this eutectic phase diagram. If you melt stainless steel, which one will go? Solid solution. When you see stainless steel, do you see individual mineral? It looks like it's made of single material, right? However, actually, stainless steel is alloy, the so-called solid solution. When you see solid solution, you can't really see two different compositions by your bare eye. You can't see that. That's the nature of alloy. They are well mixed. When you melt it, it will follow solid solution phase diagram. This is the initial composition. Temperature goes up. This is the lowest temperature that the rocks start to melt. When this happens, there is the best composition for the melt. This one, where your DI is probably 60 and your AN is 40. The best composition is relatively enriched in DI compared to the bulk composition. Even if you give more heat, the temperature will not go up. It will stay here. It will melt and melt and melt, and the melt always have this composition, the best composition. Because the best composition has relatively more DI, the remaining solid will be increasingly enriched in AN. Because the magma always extract more DI than AN, until every single grain of DI is dissolved, which is here, it's 100% AN. Then the temperature will start to go up, and the AN, which is now pure AN, will start to melt. Your magma composition will change. And that would be the temperature range of partial melting. This is liquid dust, the highest melting temperature above which everything melts. So the nature is the melt has a defined DI-AN ratio at the eutectic point here, the best composition. Now we go to the solid solution. Temperature rises. It reaches the solid dust, the lowest melting point. What happened is the magma, which is L1 here, its composition depends on the S1 here. If Fa and Fo, the ratio is 60-40 here, then the magma will also have higher firelight. When the temperature continues to rise, the solid composition will get increasingly increased in Fo, and the magma will extract in proportion to the solid composition. Now you see the difference? This one, when the magma extracts, always have the so-called best composition, no matter how the solid composition change. But here, the magma composition will change according to the solid composition. The line here, from here to here, they almost have the same width. So it's proportional to the solid composition until everything melts above the liquid dust. The nature is the Fa to Fo ratio of the melt will change depending on the solid composition. Issue of pressure. The phase diagram were made at 1 atmospheric pressure. The higher the pressure, the higher the melting point will be. In general, for every 3 kilometers, the melting point or the liquid dust temperature will increase by 5 to 10 degrees. Mantle material usually melt in regions where they rise. Is it temperature or pressure controlled? The answer is pressure. That's the nature of rock melting on Earth. The rock always melt because of lowered pressure, which is what we call pressure release melting. Melting of material because of the decrease in melting temperature. Because the release in pressure usually corresponds to upwelling of magma, which usually corresponds to lower temperature. So we say the mantle actually cools down as it melts. Here we have magma upwelling. The reason why it melts is not because it encounters higher temperature. In fact, its temperature decreases when it goes up. However, the decrease rate is lower than the decrease in solid dust. The solid dust will change very quickly with a shallower depth. At some point, its temperature will be higher than the solid dust, then it starts to melt. Ocean and continental crust. Oceanic crust is explained by partial melting of mantle. Oceanic crust is constantly being produced at the divergent zone. Continental crust is endpoint of multiple melting and cooling events. Because the continental crust has 70% of silicon, the silicon content is too high to be explained by a single melting event of the mantle. That means the mantle has melted once, solidified up some layer, and next time it will be melted again, starting from this new solidified layer. It will be further extracted to form new magma, and the final product is the continental crust. What type of file tends to enrich in continent? Magma file will be enriched in continental crust. That is what I said. The continental crust has too much silicon. Therefore, from here to here, is difficult to be achieved in one single partial melting event. It requires many different times of partial melting event to change its composition from here to here. So next week, we are going to talk about plate tectonics. I don't know how you learned plate tectonics in your high school, but I think if you read the textbook, you will realize that the plate tectonics that scientists know since 1980s is sort of different from you learn from your high school or from what I learned from my high school. For A students, does plate geometry correspond to mantle convection cells? Read these pages and answer the following questions. First, what is the problem with the boundary of African plate? This plate. Please look up the textbook or some internet material to figure out what type of plate boundary this is. When we talk about plate boundary, we have divergent, convergent, lateral. Please check what are the plate boundary type here, 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 and here. And what may be the problem? Second, why does mantle melt and upwell at the ocean ridge? Answer this plot. As a hint, to answer this plot correctly, it is related to the behavior of rock melting, how rock is melted. The way rock melts is different from our common sense. Third, why does plate subduction take place? You have to answer this. This graph shows you how scientists believe how plate subduction started. Lastly, does plate geometry correspond to mantle convection cell? Recall your high school education. When teachers talk about plate tectonics, they always come up with this kind of convection cell. Does plate geometry really correspond to plate convection cell? Does the divergent plate boundary correspond to some specific feature and convergent plate boundary correspond to another specific feature of the mantle convection cells? B student, does the mantle convect? The mantle is made of solid rock, solid silicate. Does it really convect? Because convection seems to be a concept for liquids, right? Is it also a concept for solid? So you need to answer the following question and read these pages. First, what is isostasy? This is relate our elevation models and the concept of isostasy. Second, what is post-glacial rebound? Answer this question. Third, what is Rayleigh number? So Rayleigh number is a concept from fluid dynamics. You have to refer to this equation and then explain the result of the numerical modeling, which is this graph. Then you have to answer, does the mantle convect? What do scientists think? Lastly, which geological feature would correspond to the upwelling limb of mantle convection cell? Over the past decade, this is the question that students often fail to answer correctly. However, this is the most important concept that I hope to deliver to you. Where is the upwelling limb of mantle convection cell?